I must start by apologizing to everyone for not being there, and I'm really sorry that I couldn't come this time. I was planning to come, but then events got in the way, and I don't seem to be master of my own time at the moment, so I'm going to have to do this remotely. So thank you very much for being there and taking this paper here. My first the first thing I want to say is that one of the comments by the reviewers was that the paper was too big, or there was too much in the paper. So rather than kind of revising the paper and taking a chunk out of that, I decided to concentrate on one of the aspects of the two things I'm talking about in the paper. So you can have a look at the other thing in the written form, and I think the other thing is probably written a bit better. It's more comprehensive. So you can. I'm going to talk a bit about the second part of the paper, which maybe is less comprehensive in the written part. So it will make more sense to do a presentation on this. So the whole principle, the idea of the paper was to look at C++ at this point in time and see how much can it give us as a tool for constructing musical instruments or computer instruments. C++ has been a language that I think now is reaching maturity, and I've been involved in writing C++ for the past 25 years, 25 years. And in the early days, I think there was a lot that was probably not resolved, and so I think that at this point, I think it just offers a more comprehensive proposition, even though people have been doing these things for the past 20 years. I think now it has reached the point when I think it offers musicians as well and composers kind of an expressive tool that can be used for lots of things. So in the first part of the paper, I spoke about a library that is that basically is kind of almost like a repository of components that can be used in developing multi-platform programs for computer instruments. And in the second part of the paper, I'm talking about how you could embed components of instruments in a music programming language like C Sound, and take from a perspective of C++. So this is part of this new framework that we're shipping now with the next version of C Sound, and that would allow people to use C++ in an expressive way to write opcodes. So it's called C Sound Opcode Plugin Framework, and to find a cute a kind of pronunciation of it, I went back to Portuguese and I call it cipó, which means vine and rope, and it means that you can both bring yourself up a tree with it, or you can hang yourself as well. So we have to be aware of that condition. Is everyone here listening all right to me?
Perfect. Yeah.
Great. Okay, let's go. So let's talk a little bit about it. So first of all, C-Sound has a fairly straightforward plugin mechanism, and the fact that it has over 2,000 opcodes means that it's fairly easy to add things to it. Many of these have been added post, its original setup and so on. So it can be used to extend a language fairly easily, and so it adds new native functionality to the system. And beyond other things that you can do, which is to write, extensions using Faust or using Lua and using Python. But this is kind of the native functionality that can be extended. So it is a C language interface because C Sound is written in C, It's not written in C++. It's written in C, and all the mechanisms inside C sound work using C language. And so when we're thinking about putting a C++ layer on top of that, we have to be mindful of all the things that are not C++. And because the core system doesn't know anything about C++, we can't just go ahead and use stuff that C doesn't understand, and it's only within C++. So we really have to be mindful of that. And we'll see some examples of this as we go along. So next thing is that why would you want to do if there is a very very functional system in C which does everything that you need, why do you want to use C++? Well, today I find that especially with students, that students kind of seem to be barking at the idea, or barfing at the idea of using C. They want to use C++. They seem to think that C++ is more accessible language. I have doubts about that, but that's some perception that exists there. Because it is much bigger and it has a lot more conceptual complexities in that. For the kinds of things that much of the bread and butter stuff that you would do in signal processing, a lot of that, it might be just obscuring rather than clarifying things. But anyway, so why that? Why? Well, because of that. Because people want to use it, and I think that there are advantages that you can, for instance, reuse code, and we're going to see an example where code reuse becomes really, really handy. And I think that for certain things, I think it could be really positive. So there are scalable qualities to it as far as complexity and so on. Okay, so it's a different style of programming as well. So providing a kind of a range of idioms for people to relate, to develop things for the system. Now, we need to point out that there is something in this vein already, and has been there for a good while. It's provided as a kind of a thin layer on top of C, kind of that underlying the C language function. And it has been used in the code base and so on. But I had trouble using it. I don't think I have problems with it. So I thought that rather than trying to fix it, and since it's not my code, I prefer to provide a fresh start, so that it could be designed from the ground up, and then took my time to sort of design it in such a way that it can be extensible as well as we develop. We can extend the framework for the parts that we need. And it uses templating heavily to provide quite a lot of reuse. And of course, as we see, there are a few things in C++ that doesn't make sense to using here, but there are other things that make sense, and we make those choices as we go along. So before we actually go into the framework, I wanted to have a little, give you a little flavor of what is the original C Opcode API, and it's only a little part of it in a way, because although it's very simple on the structure, if you want to do certain things with the system and to use some of the resources of the system, you need to dig a little bit deeper. But let's have a look at this, what it is, so you can have an understanding. Then you have an understanding of where I am coming from when designing the CPOR. So adding an opcode to sound in C will involve three things. And some of you know that, some of you don't. And for those of you who don't, basically three basic things which you expect to have in a plugin, which is a data space, which is kind of a data structure that will basically have what is the kind of common aspects of which is the base of the opcode. And we'll also have the pointers to inputs and outputs of an opcode. And then if you have any state variables, you add to it as well. And stuff, anything that you need, then you add to this data space, anything that needs to be permanent between, when you start the opcode and when you finish the opcode, they're there. And then you have the functionality, actual functionality is given by 3 functions, which you will use to compute the initialization time. So basically, when you start the plugin, an instance of the plugin, instance of the opcode, it will start and will run the code then, and then when it just runs once. Then you have the performance time code, which is basically the processing code, which there are 2 variations. One that is designed for processing control signals. The other one is designed to process audio signals. Even though the kind of separation between the 2 is kind of very thin, but there's separation there. And then you have a bit of boilerplate code that you use then to tell Csound that the opcode exists. So when this is offered as a dynamic library, so when the dynamic library is loaded, then Csound registers it and then makes it available to the program, to the Csound program. Okay. So one startup, then Csound will find our plugins, register them, and with the system, and that will be using the boilerplate code in 3. If the opcode is using the code, so you write your little Csound program that is going to be running. When the opcode is instantiated, so a running instance of the opcode is running, then there will be a location of memory for the data space. And then the processing functions will be called. You could be the initialization times code, and then if it's running to produce signals, then we call either the control or the audio signal functions. So that's how it works. So it's generally straightforward to write simple C opcodes. Complexity, as I said, will pick up when you need to use resources and from the system, such as if you need to do a lot of memory location, if you have function table access, if you want to access different variable types from the simple ones, for instance, arrays and spectral signals and so on. And if you want to invoke FFTs and stuff like that. Then the reason the complexity is that you're going to have to then invoke functions that are provided by the Csound engine, and you have to know how to do those. And it's just a little bit more complicated. So here you is the example of code for this, what I was just saying earlier. So you have at the top, then you have the header file that has all the definitions that you need. And then you have to write here, as in this bit here, you have to put your data structure that contains the data space. And the first element of the data structure, it's mandated to be the OPDS, which is the code base. You can call it whatever you want, but it has to be there. Otherwise, it won't work. And then you have a bunch of pointers, which will be your arguments, your input arguments. So this will work for simple, for the standard variables, which are just signals or scalars. But if you want to have something more of the advanced types of variables, then you have to use different types of pointers. That would be pointers to data structures. So my float is just a definition of a floating point number, which can be either 32-bit or 64-bit, depending on the version of Csound that's being running. So this is the point 1 of my 3 things. And the point 2 of the 3 things are 3 functions that you can call them anything you like, provided that they have this signature here, which is the opcode, the Csound engine pointer. So the engine instance that you run this opcode in, and then the data space for the opcode. And then you write your init kind code, and you return an error code, which is often the 0 or non-zero. 0 for okay, non-zero for no okay, not okay. And then you have this sort for initialization. This is for control signal processing. So this function is called repeatedly to produce control signals, which are scalar outputs. And then this one here would be for the case of audio signals, where you're producing vectors rather than scalars, or consuming vectors. So here, then the number 3, which is the boilerplate code. You have to define an O-entry, couple of O-entry structures that you put in that you're going to provide for the C sound, giving the name of the opcode, the size of the data space, when it's supposed to be run, and it's a code that's it's a sum of certain codes. If you're supposed to run at initial time is 1, for audio is 4, and for control is 2. So it's going to be either 1, 3, 1, 2, 3, 4, 5, or 7. So in this case here, this opcode, first opcode here, is containing, it's running at audio rates and init time. So it's basically contains the perf function here, the init function, and the perf function, and there's no control function for it. And then I have another opcode. So it's basically the same opcode, but polymorphic. So you can runs for control signals and audio signals, depending on the control signals that the variables that you're using with it, and that's basically passed there, the same thing. And you have then a macro here that takes this local ops variable and registers with C sound. So you don't even need to know what's behind that. It's just boilerplate. So that's simple enough, but it is C. I don't have any problems with it. I find it fairly straightforward, and I'm happy to use it. But it doesn't have the facilities that some people might be wanting, and in C++. So you could potentially use this within a C++ context. It would compile within a C++ context, and you could add other things to do that. But then if you're using C++, then you may as well go all the way and start providing a whole framework so people can avoid having to replicate code and have all the facilities there more easily given. So that's the next thing then. Okay, so this is the original, and now let's talk about CPAW in the API and the basics for the API. Okay, so bearing in mind the things I said before and in the structure of the opcode in C, you're going to see a lot of things replicated here, but you will see how it sort of has this dressing C++ that will make it slightly different. Okay, so the CPAW API is built on top of this tripartite model. That's because it's given, so you won't modify it. You wouldn't be able to do it otherwise. We have to change the engine in order to do that. So we don't do it. We catch a ride in the existing system, on the existing model. So we're going to employ significant code reuse using templating. So that those three elements that we have given you will basically reduce to two. You're going to have a class that will define the opcode. It is already a class, by the way, but it's written in C, and a class in C has to have separate things, like you have to put the data structure and the function separately. But here, because it is C++, and you have everything in a single block, and then a call to registering function, which is a template function. And that simplifies a lot. You just call the function, and you don't need to be kind of worrying about certain things. It looks better anyway. We'll see. Okay. So here we go. This is the minimal opcode in CPAW. You have to include the plugin.h is the header file, and all you need to do is derive a class from plugin and instantiate, because it's a template, base class. Instantiate it with the number of inputs, so number of outputs and inputs. So one output and one input. So this is basically how many arguments you're going to have. So this is a kind of a minimum non-op opcode. You could create it, Csound will load it, you run it, it won't do anything, but it would satisfy everything, all the requirements for an opcode. So if you want to do something, then we need to start adding processing methods to the class. And I see that my processing has become a little bit hissy there with 3 S's. Right. So as we saw, in Csound, an opcode can be active at the init and or performance times. So you can have an opcode that just runs at init time, or you can have an opcode that runs at init time and at performance time. So the init code, as we saw, is run once. So when you instantiate or the opcode, so that's normally if this is inside an instrument, it's when instrument is started, is instantiated. But if it's outside an instrument, it's just once when that code is compiled. So perf time code runs then repeatedly when Csound is processing audio or control signals. So it's like it'll be called in a loop and produce the output. So for each one of these actions, you have init, control, audio. You're going to have to provide a computing method. So in the same way that you have to provide functions in the C interface, you will provide a method here. You don't need to provide them, but then that bit will not be done. But these are the things you need to do. So here it is. For instance, the init method for an opcode that runs only at initialization time. So it just has a single init method. It doesn't have the performance or audio methods. In fact, it does have that because the base class has it, but you don't. The base class is a non-op method, so you don't really use those performance or audio performing control or audio performing methods. So they won't do anything anyway. So what you're doing here is interesting. You're not actually specializing so much, but you are shadowing the technical terms, you're shadowing the base class method. Now, shadowing is something that's not really done in C++ normally, because it causes all sorts of problems if you are instantiating your classes and you don't know what method is coming from where. But in this case here, it works perfectly, because you won't be instantiating these objects. Csound will do it. And Csound is C, and it doesn't know anything about C++. So you couldn't use a virtual method system because it would work. C doesn't know anything about virtual methods. But because Csound is instantiating this, you can basically set up your functions and allow them to shadow others without any problems. You could use the method that is sometimes called as the curiously templating method or something like that, which is to set up a kind of a template-based class and then do other stuff so that you kind of create the virtual method system using a a template like base class. But that is complicating because you don't need that. That would only be useful if you were to be instantiating those classes in C++ yourself in a program, but you're not doing that. C-Sound is doing that for you. So we don't, we can simplify it and we make it very simple. Now, in this code here, what's happening is that you're picking up the first argument, input argument, and you're copying that to the first output argument. There's only one argument anyway. There's only one parameter, and for input, one parameter for the output. So those are the only ones you can use anyway. So you're putting from the first for input, copying to the output. So this here, we will see, these are objects that are provided by the base class that will contain your arguments, and you can use an overload operator to access the actual data in it. I will see that in a minute. Okay, so here is the example, the same example, but running only a control, a perf time, a performance time, and control time. So it doesn't run at initialization time. It only runs at the perform time, or at least you're only implementing the performance time function for control signals. Okay, but it's doing the same thing, but that's doing constantly. So picking up an input control signal and copy it to the output. And finally, this is the one that does audio. And it's slightly different in the sense that you're not dealing with single called scalar variables. You actually parameters. You're actually picking up a whole vector, and you're copying that to the output. And I'm seeing a typo in the code anyway, but don't worry. It should be inargs 0.begin and inargs 0.end because it's the beginning and the end of the input array that's copied into the out args. And as you see, this is an overloaded operator that gives out the pointers to the start and the end of to the start of the array and at the end, and you can use an iterator to do that. So that's copying the data into the output, even though my code is wrong there and got mistyped. So this is how it's done. Now, okay, so this is the first part of things. You create your code, your class, you add the processing function, and then you register it. So to register it, you call a template function that takes the class as its template parameter plus the name, argument types, and action thread. So you need perf or audio, kperf. Okay, and then this template function then is going to be called inside an onload function, which is the entry point for the plugin library. So you create an entry point for the plugin library. It has to be called onload, and there you put your template functions. So here it is. First of all, you have to add in a header here that has some definitions that you need for loading, and then onload is called and it is implemented, and that when it's run, then CIEREC will load and run this function, and will register the opcodes. As you can see, it's very, very simply registered. You have have to pass the C-Sound engine here. C-Sound engine here, the name of the opcode, the input types, the output types, so I types. These are the C-Sound variable types. And then when it's supposed to be run. So if you say I is just initialization time, if you say K is control time, and if you say A is audio rate. So perf control and perf audio. So you can be I, K, or A, or it can be IK, IA, or IKA. So those are constants that we can use directly there, and they are very easy to remember. Instead of having to remember numbers, you remember the constants much simpler. Okay, so that's the basics. So let's have a look at some of the important base classes that we'll use. So we saw that basically the Opcode base class plugin is derived from is provided for you to derive your own plugin. It comes from the OPDS class, which is actually a C structure, but it's derived straight from that. So you don't need to worry about that. It's like it's completely embedded into the system, and then this has a number of facilities that is important to note. We have already seen the out args and the in args, which are params objects, and we'll talk a little bit about params objects in a minute. But also there is a C-sound object, which is the C-sound engine object, has an offset, which is used as a starting position of an audio vector. So that's given by C-sound when the code is run, and nsums, which is the size of an audio vector, which is also used only for codes. So this offset here is in nsums can change from because that gives you gives C-sound the sample accurate mechanism. Okay, so here you can see then that there isn't actually not only the plugin class, but there is also another class which is derived from plugin, which is called fplugin, which is more kind of adds a little thing, which is another variable, not a member variable that keeps a frame count, and that's used for streaming frequency domain plugin. So instead of deriving from plugin, we derive from fplugin, so that we can take advantage of this frame count as a specific thing for that type of code. Okay, so let's talk about the params objects. So arguments are going to be provided as two arrays of params objects. The param class then is kind of iterable, so it has all sorts of all these C++ facilities. So you can iterate over the parameters and so on, and you can access it using the operator, the kind of indexing operator there, and so you can access each argument as a floating point number. You can use that for scalar arguments, or you can use the operator function operator, which is also replicated in the data function, the data member function, which allows you to access the value as a pointer, as a float pointer, and that can be used for vector arguments. We can use also, there's other access. So if you want to do spectral data, you use fsig data. If you want to access string data, you use string. So those are different types of C-sound variables that you can access with, then vector data for array variables. So those are the internal types in C-sound. So when you're using numeric arguments, we saw that it's fairly easy, and you can just manipulate the take directly from the argument the value of it. But audio signals are vectors, so we kind of can get the raw pointers from them and use them. But we also can use the kind of a wrapping class, which is really useful because it gives you the audio signal in a kind of more with some facilities that can allow you to go iterate over it and do other things. So this audio sig is basically takes in a pointer to the base class OPDS. Basically, it's the pointer to the plugin that you're developing, but it's because it's polymorphic. So you can you take pointer to your plugin, existing plugin object, and you have a pointer to actual raw pointer, and then a switch there to reset. So basically, that can clear the output if you need to clear the output buffer that you're creating. So it's just a wrapper, but you'll see that it will make things much simpler. So those are that's the framework in a nutshell. That's the framework. Around the framework, there's a number of support classes. So say the toolkit part of it that allow us to do quite a lot of stuff. So let's have a little tour of the support classes. Now, in C Sound, memory allocation is handled by the core, by the engine, because it's quite efficient in the way it treats memory, and it's also prevents leaks and undefined behavior. So it has its own memory allocation mechanism. And we should not use C++ allocators, otherwise you're going to get in complete tangle, and you're going to probably hang yourself with using. So C++ allocators are not allowed, because the whole thing is in C and it's going to cause trouble. So don't. So in order to do that, I kind of provide an allocator mechanism that is wrapping the C Sound allocation mechanism. If we follow these rules and use this allocation, then we won't have any problems. We have C Sound has this alloc mechanism, and we wrap it up with the memalloc wrapper class. It's not really too dissimilar in a way to vector, but to standard vector, but it's built into C Sound. So this Altman class then allows you to allocate memory, and that allocation only happens if it's needed. Sound, if there's a memory there, it would use it. It uses memory pools, and so it is quite efficient in that way. So you can access it with array subscript. You can get a pointer to the data. You can get the length of the vector. You can have a begin and end iterators, and you have iterators for this class. So you can apply quite a lot of C++ idioms to this. So here's an example where it's useful. Here's your classic comb filter or delay effect. It has one output and two inputs. So the two inputs will be the delay time and the audio signal. So in your init function, first of all, I declare a couple of iterators here. So first, I declare an object here that is a delay object. It's an Auxman object, and it holds my floats. So you can allocate memories for all different types. It's like standard vector. So that's our delay memory, and then I allocate an iterator for that. So I declare an iterator for that. So when we're running the initialization, we allocate the memory by calling the allocate function, and then we have basically allocated as much memory for a certain amount of seconds that I have. That's given by the first argument, and I point my iterator to the beginning of the delay line. In the performance thing, I have two. I'm taking the input from the first argument of the input, and the output is from the output argument. So these are my argument objects, or my audio objects for input and output. And here is audio processing. Now I'm using from the standard algorithms, I'm using the transform algorithm, which is fairly handy for what we need to do here. You can see I have the beginning and the end over input, and that's the output. And then I put in a lambda there that takes in each sample input and puts into memory, and then outputs whatever is in memory from the delay. and then returns the sample that it's read from the input, and goes around. Now you can see here it's very compact. I mean, it don't, and it's a real C++ idiom. As you can see, this the loop is built in. You don't have loop index, loop counters, and so on. It's a fairly decent sort of C++ idiom, and this is all facilitated by the mechanisms that we have here. That CPO gives the plugin writer. Okay, moving on a little bit. So that here's one thing that Csound has and uses a lot: tables. Tables are basically bits of memory that we use to store pre-calculated functions or to store audio or store whatever that we need to do. And accessing it is really something that Opcodes are. It's important to allow Opcode to do it in an easy way. So we have a table object, table class here that allows us to kind of access with operators, index operators, access the data directly, have iterators in a very similar way that we saw with Auxman. In fact, a lot of the code can be interchangeable. And here's an example of it, and implementing a standard table lookup oscillator. So you have a plugin with one output and three inputs. So the first input is going to be the amplitude, second input would be the frequency, and third input would be the number of the function table that you're using, or an identifier for the function table, whatever. It's given to Csound, to the opcode. So I have a table object here, which will wrap the table, and some variables that we need to use in the data space. So here we have then initialized the table, taking the third argument. You can see third argument is the table number, so that initializes the table, and then I can define what the SCL is kind of a scalar variable for, depending on the function table and the sampling rate. We'll see how that works in a minute, and initialize the x variable from 0. Then here we go, the performing function here. As you can see here, the output, we have only one output, one audio variable, which is the one audio argument, which is the output. The amplitude is taken from the first argument, so it's a control rate argument, and the frequency is taken from the second argument, it's a control rate argument, and I scale that frequency by that scaling unit to give us our sampling increment. And then we have a loop, a C++11 loop, a for each oriented or loop that loops over the output. So you can see I'm taking the output reference here, and then I'm just doing that. I'm implementing that. So again, here we see another Csound idiom. That's not C++ idiom. Which is this type of loop here, and accessing the table is directly through indexing, so fairly straightforward. Okay, let's running a little bit more quickly now. We have strings. Strings are basically a Csound data structure, and I'm actually wrapping it. I'm using it directly. So this is, for instance, an example of just printing a message that comes into a string argument. So note that there's no output, so we don't have any. We have zero outputs, only one input here. And F6. F6 are function. They are frequency domain signals. Basically, phase vocoder data, or it could be other types of other formats of spectral domain data, but phase vocoder is the typical one. So you have an fsig wrapper class for this. The fsig holds a PV frame object, which itself is a series of PV bins that actually hold the data itself. So the fsig class has initialization, has some basic things like the GFT size, the hop size, the window type, the number of bins, and there's a counter that you can count the frames, the existing frames, because the fsig will have a built-in frame count, and checking whether it's a sliding mode or not, and return. You can return the fsig as a kind of in a PVS data format. Now, the PV frame has access then to the frame itself. So you have an operator, a subscript that can access the individual components of the individual bins of the frame. You can get also the raw data, and you have iterators as well from the beginning and the end of the frame. And so that's, again, the iterators thing that make it very useful. And that each phase vocoder bin is a PV bin, and that you can access the bin amplitude, can access the frequency, the bin frequency. You can set the bin amplitude and bin frequency. You can, there's a couple of arithmetic operators to multiply the amplitudes by now, so you can scale the bin amplitudes, and there is also some unary versions of that. So here's an example of the opcode, and interestingly here I use I can to simplify. I can actually add the types to the package the types of arguments inside the opcode. So here are two inputs and one output. So I can say that the output is F and the input is FK. If we do that, then we can, when we're registering the opcode, we can use a simplified version of the registration that doesn't even need to take the types. Types are packed in with the opcode. So this is quite useful for certain applications. Here's the initialization. There's a bunch of things there. And we initialize the output frame, output fsig, here using the input fsig data. And then performing interesting is a K rate performance, because it's actually not running a K rate, it's running at the frame rate. But we call this, we normally determine that this is running at the K rate just to fit in with the system. So you have the inputs here, F in and F out, and then depending on the frame count, if you have advanced in the frame count, so if your input has advanced one frame ahead, then you do the processing here. And the processing, again, a very C++ idiom here, where I'm using this opcode will basically change the gain of a phase vocoder signal. So it just iterates over the input and multiplies each bin by a gain value, G, which is the second argument here. And that basically changed the gain signal. Fairly straightforward. And then finally, to complement, we can access arrays using the vector class, which is an array dat class. It wraps up this array dat class that CSound has internally. Again, very similar things that you saw before. The same thing goes on. You have an operator, an indexing array subscript operator to access it. So you can access the raw data. You have iterators to the beginning and the end, and iterator types. Here we have an example of an array. That this is a simple example that just basically picks up an array and copies it to the output. In performance time. So here you have an array object, an array of my floats. You could have an array of PVS dot, for instance, which is phase signal, or you could have an array of strings or something like that. But in this case, it's an array of numbers. And I'm copying the input. Now it's correct here, you can see. I'm copying the input of the array to the output. And this has the correct beginning and end here. Okay, so a bit of a marathon, but we reached the end in time. And then just a final note here that if you want to build your codes with CPO, you only require a C compiler that has C++11 and the public headers, which we include plugin.h. The code then is built as a dynamic or as a shared library. So as so in Linux or the UILib in OS X and DLL in Windows. And CPO then CPO does not really impose any link time dependencies. So it just builds with no so there's no link dependency, you just need the headers. If you want to know a little bit more, you can look at csound.github.io. And of course, everything is there, including in the repository. There are some examples and some further kind of documentation in the form of Doxygen generated files. Okay, thank you very much. That's it.
Thank you. Thank you, Victor. Are there some questions?
Hi, Victor. This is Jan. So thank you for your talk. C++ was more or less fall asleep during many years. So since C++11, there is a lot of new things. And from your point of view, what are the new things, the new features that could be very interesting for... so you demonstrated how these features can be interesting to provide the framework for opcodes, but for the DSP part. And a related question is, in the example, in the delay example, is the code generated from the C++ code exactly as efficient as the C code?
That's a good question. I wouldn't, without measuring it, I can't say for sure. But I'd say that modern C++ compilers are very good thing, very good things. So they would, with the extra hints that you add, I think that would be it should be efficient enough. So when you look at just a very simple example of an oscillator, I can't see that, for instance, that this oscillator here is any less efficient than a C written oscillator, and equally this delay line here, it should be fairly efficient, but you never know. I mean, this was always my my doubt with relation to C++, whether, because I kind of didn't trust that the code that I wrote in C, which is much closer to the metal in a way, would be not as efficient if I had written using this type of idiom here. But I think that because there's such a lot of hints about what this is and how this should be, that and I would trust that a modern compiler would look at would translate this into a very efficient bit of code.
Okay, thank you.
But it's important to say that I think that it's probably the efficiency probably wasn't there earlier on, and especially not in this case here where the underlying mechanism is C and you only actually writing your C++ code that's actually called by C. But when you actually wrote the whole program in C++, and you will start using things like copying objects. The horrible things could happen there. You'd have really inefficient code, and there has been quite a lot of move into quite a lot of change in the last, especially with C++11, with move semantics that make things a little better. But you can, if you start using certain things in C++ in signal processing, like for instance copying objects and not realizing that maybe the code is, every time you call it, it's allocating a new object and then copying it and doing things like that. They still can happen, and that can be, can be really inefficient. It's not very good for for signal processing. So you need to be aware of what you're doing. And that's this comment, I think, is to do. It comes back to that thing about giving you enough rope to hang yourself. It does really give you enough rope to hang yourself if you're not careful. Okay.
Okay. So, thanks you.
Thank you.